This is going on page 23. When we're done, we're going to start with a little bit of a review from geometry and connect it to what we're doing today. So right here, I want you to draw a circle the best you can. For me, that's a pretty darn good circle, but it's okay if it kind of looks like an egg. You can pretend. Okay. So draw a circle up there in the blank spots there. All right, and then you learned that if you have a line that intersects the circle at exactly one point, what do you need, something to write with? Go in the back counter. There's pencils back there, there's all kinds of stuff. If I have a circle, or if I have a line that intersects the circle at exactly one point, can anybody tell me what kind of line that is? It's what? Tangent? Good. So this is a tangent line. You also learned about a line that intersects the circle at exactly 2 points. Do we know what's that? That's called secant. Okay, this is a secant line. So if secant and tangent. You also heard tangent related to something else in geometry that seemed completely unrelated to circles. Anybody know what that is? What else was the word tangent used with? Trig? Does that sound familiar? SOHCAHTOA? Yeah. And so it seems completely unrelated to circles. It's actually very much related, and you will see that relationship here probably before the end of the semester. But so you learned the tangent line intersects a circle at exactly 1 point, secant at exactly 2 points, which makes sense because all lines are straight. So saying you have a straight line is redundant. You don't need that. If the pen doesn't work, some of them are crappy. Throw it away, get another one, or get a pencil. I didn't test them. I just put them back there. Because all lines are straight, so you don't even have to say that. It's not going to loop back around. Don't put that one back. If it doesn't work, throw it away. Okay, so then, but now we're not really talking about circles with these lines right now. We're going to be talking about functions. So I want you to draw a function. Looks something like that. It's okay if it's not exactly the same. Something similar to that. And the tangent line here, if I had a line tangent to this, and I kind of mentioned this the other day, if we're talking about speed, right, and I want my speed right at 3 minutes, like I want that speed right then I want my rate of change right there at that point, okay, that exact point right there. Then the rate of change, which we know as slope, on a curve, we know the rate of change changes, right? But if the rate of change at that point is actually going to be the slope of the tangent line at that point. Okay? And just do your best to make it look tangent. I mean, technically, I think my line's not even touching my curve, but you get the idea. So, my tangent line, my line there, touches that curve right there at that 1 point. Does that line intersect that function at exactly 1 point? It doesn't, right? Because lines go on forever, yes? And so when it keeps going, it would actually intersect it again over here, right? But it's still a tangent line. Because a tangent line related to a circle, yes, it intersects a circle at exactly 1 point, and that word exactly is important. My tangent line doesn't have to intersect my function at exactly 1 point. It does have to intersect the function at exactly 1 point in this neighborhood right here. Like if I was to limit my domain, that little neighborhood is just right there. Or I can think of it as the line through two infinitely close points. These 2 points here, not even remotely close to each other. 2 points right here, infinitely close to each other, means it basically makes it just that 1 point. Okay? So I just want to clear up some misconceptions sometimes with, well, this can't be a tangent line because it's going to intersect again. You are right. But when we are looking at these, and because remember, this is not something I can find without using calculus. And when you actually use the calculus to find that slope, we always have a closed domain. I can't come up with the word. A restricted domain. Good Lord. A restricted domain where we're just looking in that little neighborhood, and what's happening over here doesn't even matter. We okay with that? Okay, so like I said, if I actually want that slope, we don't have the math we need quite yet for that, but because we don't know how to find the slope with just 1 point. That requires calculus. But I can find the slope of a line between 2 points. So if I have these 2 points here, then I have this secant line, right? And even that secant line doesn't intersect that curve at exactly 2 points because it could intersect again. Now, depending on the curve, the tangent line could intersect at exactly 1 point, and the secant line could intersect at exactly 2 points. I just want to show you this to know that it could be different, but we don't really care about what's going on over here right now. You with me on that? So we know so this is still a secant line, and this is still a tangent line. All right? And we know how to find the slope between 2 points. You've been doing that forever. I think you might even start that before you hit up number 1. I don't know, but that should be old news. And I can use the slope of the secant line to estimate my rate of change at that point. So if I did find the slope of this secant line using 2 points on either side of it, that would be an estimate. My actual picture, I think it wouldn't be a great estimate, right? But it would be an estimate. How could I make my estimate better? How could I change my secant line to make a better estimate? Any ideas? Could I move my points? If I moved my 2 green points closer and closer to the purple one, right, then it would be closer and closer. And I could actually find a point over here, maybe like right here even, that if I drew that line, they'd be parallel and they'd have the same slope. Or I can get really, really close on either side and do it that way. Okay, does that make sense to you? And that's how we go from secant to tangent. But I'm going to use those words today. They're not actually typed in here. I want to make sure that you understand how they work on the curve. Okay? Everybody good? Yes? Okay. So some of this that we're going to talk through, and these notes, I know some of them are very wordy, and I kind of like fill in the blank notes, and I chose not to take stuff out and make you fill in the blank because we're going to end up doing a whole lot of writing anyway. So make sure you're paying attention and your eyes aren't rolling the back of your head when we're just talking about stuff, and that you're actually underlining and circling so that you can go back and find the important stuff. All right, so in 1-1, what we just spent 3 days doing, says we learned the rate of change. The phrase rate of change is synonymous with slope. I don't think we actually learned it. I think you already knew it. But rate of change and slope, same thing, right? So and we know that a positive rate of change means we have a positive slope, so the function is increasing. We know that from our fun chart, right? Positive rate of change, function is increasing. And a negative rate of change indicates a negative slope, and the function is decreasing. That's kind of old news too. You just never really looked at it in a fun chart or had to connect it that way. Okay. Looking ahead to calculus. In AP pre-calculus, we will define the rate of change of a function at a point as the rate at which the output values would change if the input values would change. So change in y over change in x, that type of thing. Later, in AP calculus, or really in any calculus, AP pre-cal is kind of, meant to be before AP calculus, but I realize some of you are seniors or some of you might be in early college and you don't actually take AP calculus, but you'll take calculus. All this still kind of, it all still applies. All right, so you will call this instantaneous rate of change. Like, what is my rate of change at that instant, right at 3 minutes? The concept of the function changing instantaneously is called a derivative. We'll talk about those a tiny bit at the end of the year as we get closer to calculus. And it's quite challenging to understand without first learning the foundational ideas in AP pre-cal. Okay? All right. So, in AP pre-calculus, we are unable to find the rate of change at a given point. I've said that multiple times. That requires calculus. But we need to determine if the rate of change at a given point is positive, negative, or 0. We will also need to be able to compare the rates of change at 2 distinct points. So we do have to figure out some stuff about it. We won't be able to say, hey, at that point, rate of change is 12. But we can say rate of change is positive. That's something that we'll be able to figure out. Okay? So, AP exam insights. When considering rates of change at a given point, it might be helpful to think about the graph as a roller coaster, right? If you're riding in a roller coaster, if you're going up, then the function has a positive rate of change at that point. If you're going down, the function has a negative rate of change at that point. And that's really kind of helping you think about positive and negative rates of change, or positive and negative slope, which again, I think that we have, I hope anyway. So if you look at these little cars, so this is like a roller coaster. Think about, you get on the roller coaster, and so we can draw that tangent line. And you're going up, and it's going click, 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 kind of slow. And you're like, this is nice. This is going to be so fun. I'm so positive about this ride. And then you get up here, and what's the slope right here? What's the horizontal line? What's the slope? 0, okay? You get up there, and you're in between going up and going down, right? And then when you're actually going down and you're terrified, now you might have a negative feeling about getting on the thing in the first place, okay? Maybe that's the way you can remember what's going on. I don't know. But so at the instant, the point when you're at the top of the peak or the bottom of a valley, your maximum or your minimum, you are not moving up or down. At that single instant, you are changing between going up and going down. At these points, rate of change is neither positive or negative. The rate of change is 0. But we know that about a horizontal line also. So not new information, just a new way to connect it to other things. Okay, that's one thing I want you to remember, is that it's not like you've never heard of slope before. You just haven't talked about slope like this. So don't look at it as a whole big unknown type of thing. And then it just shows you kind of basically what we were talking about. This is positive, this is 0, this is negative, okay? And then here's a little fun fact. The fastest roller coaster in the world is the Formula Rossa in Abu Dhabi, the United Arab Emirates. Built in 2010, the coaster reaches a maximum speed of 149.1 miles per hour. For comparison, the average speed for the 2008 Indy 500 was 143.6 miles per hour. I love roller coasters, and that sounds terrifying to me. I mean, honestly, I don't know how fast the roller coasters I've ever been on go, so maybe it's not that much less than that, but that sounds terrifyingly fast. And your life is in the hands of the engineers that built these things. We hope they understood their calculus, and we hope that they didn't mess up on their decimal points, right? Otherwise, you're going to go flying off that thing. All right, flip it over. The figure shows the graph of the function f in the xy plane with 3 labeled points. We're going to order the rates of change of f at the 3 labeled points from least to greatest. So I'm also on the assignment asking you to draw in the little tangent lines. So let's go ahead and do that. And remember, if you don't actually touch it, like I didn't just then, get close enough, it's fine. Like they don't have to be perfect. It still has the same idea. Because sometimes it's hard to get it just through one point, and especially with these pens, I can't always aim right. All right, so before I even think about ordering them, I'm going to think about what I know. I don't know what the actual slope is at A. I don't care. Is it positive or negative? Positive, okay. What about B? Negative. What about C? 0. Okay, now let's pay attention to what the question says so we don't do it backwards. We want to order them from least to greatest. So which one has the smallest slope? B, because it's negative, right? Then C, then A. Okay, we good with all that? Easy enough? Yeah. Don't let the fact that this class is called AP or that it's called pre-calculus make you think everything's going to be complicated, because it's not. And if you approach everything like this is going to be so hard, you've already psyched yourself out. You with me on that? So sometimes things are fairly simple. We just have to have a good understanding of slope, and we're fine, and we should by now, no matter what level you're at, actually. All right, let's look at example 2. So here it says, the figure shows the graph of function g with 4 labeled points. Of the following points, at which is the rate of change of g the least? So go ahead and draw in your tangent lines. And then on something like this, I think for me anyway, instead of, I mean, I could label them up there, but I think I'm also going to label them over here. Does A have a positive or negative slope? Positive. What about B? Positive. C? Negative. D? Negative. Okay. So based on the fact that I want it to be the least, I can eliminate A and B right now. Okay. Between C and D, which one is the least, do you think? D, because it is the smallest, and if you get that mixed up, remember that right here we'd have 0, right? Then it becomes negative, then it becomes more, which makes it smaller. Okay, we good with that? Any questions? All right, good deal. So we do have one more sheet of notes. Sometimes I pick them both up, sometimes I don't, and just because you've already had so much paper shifting around your eyes, and I don't want anybody getting all mixed up on this. So if you want to go ahead and tape in the first one, you can, or you can wait until you do them both, whatever works for you. Also, if you have your AP contract, just get it out and put it on your table. I'll come get it after y'all leave. Okay. So this is also going to go on page 23 when we're done. Oops. Yeah, I'm going to let you get it because I feel like an old lady when I've been down because my back hurts so bad. Okay. So another important concept, so we talked about that instantaneous rate of change at a point. We are also going to talk about average rate of change a lot. Okay? Average rate of change of a function over an interval. So here's one of the biggest difference. The other ones was a rate of change at a specific point, at A or at x equals 3. Average rate of change is over an interval. So it would be over the interval from 1 to 4 or something like that. That would be like our secant line instead of our tangent line. All right? It's the constant rate of change, which is old school slope we know how to find, that yields the same change in the output values on that interval. It's the ratio of the change in the output values, those are what we call our y's in our formula, right? And to the change in the input values over that interval. So slope is delta y, the change in y, over the change in x. Okay? We've seen it that way before, right? Change in y over change in x. We will look more closely at the average rate of change of functions in 1.3, but we will do some of that today. In this topic, we'll approach average rates of change in a way that is very similar to how we approached the rate of change at a given point. We will determine if the average rate of change over an interval is positive, negative, or 0, and we will compare the average rates of change over two distinct intervals. Okay? If that continues forever, you can silence it and it's okay. All right. We're good on that? So let's look at this one. The figure shows the graph of the function y equals h of x, on which interval is the average rate of change of h the greatest. Okay, so I want you to remember that these intervals that are written in inequality notation could be written like this. And these two things mean the exact same thing, right? You could see it either way. If you're writing it, I want you writing it the way I did in pink, but you could see it either way, so make sure that we understand it both ways, okay? So when we're going from 2 to 3, when x is 2, here's y. When x is 3, y is right there. Well, I missed a little bit, but you get what I'm trying to do. So from 2 to 3, tell me, is the rate of change increasing or decreasing? What do you think? Increasing because it's concave up, right? And here the rate of change is negative, then the rate of change is positive, right? Because of the fun chart. Now that's not what this question was asking, but it's asking us to compare the average rates of change. So that means I want the slope of the line through those 2 points. What is the slope of that line? 0. Yes. All right, so then we go from 3 to 5. Here's 3. Here's 5. There we go. Pretend like that's straight. It's fine. We do a lot of pretending. I don't know the exact number, but is it positive or negative? Negative, okay. Then we go from 5 to 7. Looks like that. And positive or negative? Positive. And then we go from 7 to 8, which is about right there. And that is what? Negative. Okay, so we want to know which one is the greatest. So what is our answer? C. Okay. Everybody okay with that? What questions do you have? We're all good? Awesome. All right, flip it over. So the graph of the function y equals f of x is in the xy plane. You know, I know sometimes when y'all read that, you're like, wow, what the heck does that mean? It just means we have a function in the coordinate plane you've been graphing stuff in your whole life. That's all it means. It always has a negative rate of change. Which of the following definitions for the variable of x and y would best model the function of f? So I think for each one of these, we need to read through them and we need to kind of sketch something that might sort of follow that. And I say might sort of because, I mean, we could draw something that's linear. We don't necessarily know that it's linear, but at least gives us an idea of what the slope would be, okay? So let me show you what I mean. Let's read A. So for A, it says the x is the age in years of the young child. So that's going to get bigger, right? As you grow older, the height in inches of the young child. So as x gets bigger, what's happening to y? It's getting bigger also, right? Probably not linear, but enough for us to know that that is a positive rate of change. You with me on that? That's just kind of where we're looking at that. So this is a positive rate of change, which means it says always negative. I'm thinking it's not A. Okay, so then we look at B. The total number of points scored in a basketball game, so we hope it doesn't stay at 0, right? We hope that gets bigger. And the time remaining in seconds. So as the number of points go up, what happens to the number of seconds in the game? They go down. So to me, that looks like a negative rate of change. Would you agree with that? So I like B, but we're going to read the rest of them, especially when there's tons of words. C, we have the time in seconds since a ball was thrown straight up in the air versus the height of the feet and the height in feet of the ball. So when I throw the ball up, right, as time goes on, the ball is going to go up in the air. Is it going to stay up there? No, then it's going to come down, right? So I actually here have a positive rate of change and a negative rate of change, but this says always negative. So do you like C? Nope. All right, so let's read D. The radius in meters of a circle in the area of the circle. Well, as the radius gets bigger, what's going to happen to the area? It gets bigger, so that's positive also. So the only one that was negative always would be B. Okay, you see how to think through that? And you see how actually sketching pictures that you know are probably not 100% right, but can help you wrap your mind around it, it's not that big of a deal. If all you do is try to read all the words and stare at the words, that's what you're going to be doing, is staring at words, thinking, I don't even know what's going on here. So don't be afraid to sketch little things out. Okay? We good? What questions you got? All right. So I want you to grab your calculator, turn it on, and I've got some good news and bad news. The good news is I have maybe. Oh, no. Okay. Well, the bad news is maybe I can't pull this up. Oh, my goodness. All right. Well, because of the record, there we go. The good news is of course, I don't know if I can get this back up. Okay, I can. I have a big one to model this for you. The bad news is this doesn't work exactly like yours because this is the online version, because the desktop app is not, all of a sudden didn't work. And that's what I was talking about before class. Last year I thought my head was going to explode because I was like, well, I can't do exactly what you're doing. And so I'm going to do my best to talk you through this. So when you turn it on, you should be at a black screen. Yes? Everybody there? Okay, now, if you get off on what I'm doing, please tell me before I'm 10 steps down the road. That's when I get frustrated. If you accidentally hit the wrong key so you had to go back, I totally get it. Tell me to wait or ask me where you're supposed to be because you're confused. We good? So is everybody at a black screen? No. Okay. What's your malfunction here? You gotta, okay. So just hit on. There we go. All right. So we're going to do some settings first. And if you have yours, you should only have to do this once. If you start getting weird stuff because you maybe did some weird stuff to your calculator, maybe we need to redo the settings, but we should be fine. So we're at the black screen. The first thing I want you to do is hit 5 for settings. Okay. Then, and you can, so here's the other thing that I can't always make work on the board is that you have a cursor. I don't even know if my cursor works, but you can kind of, this is like a touchpad cursor that you can use. But on these things like this, I would just push the buttons. I think it's easier. Okay. Then hit 2. Now, it's possible your settings are already correct, but maybe not, so we want to make sure. This display digit should say float, not float 6, float anything, just plain old float. Okay. The angle should be radian. Exponential format, I'm checking something real quick. Normal, I had a weird, real or complex, we want it to be real. Your calculation mode should be approximate. And I think the rest is fine. Vector and decimal, yeah. Okay, we all good on all that stuff? Now, before you do anything else, your screen might look a tiny bit different than mine. At the bottom, you might have something that says make default. If yours says make default, hit make default, then OK. If not, you can just hit OK. Yeah, so you click on the arrow and then change it to approximate. Yeah, and then hit enter. Yeah, there we go. There you go. Everybody good with all that? Remember, if you have make default, make sure you click make default. If you don't have make default, it will make it default. Okay, there's just 2 different versions. And the calculators do the same thing, just really it's just the setting menus that might look a little bit different. Everybody okay with that? And then we're back in the black screen. Yes? Okay. So here's where, for some reason, I can't do what you can do. But I want you to hit 1 for new. And when you do that, it probably asks you if you want to save whatever else was there. Say no. And then you should be at a menu that looks like this. Is that where we are? Everybody there? Are we all good? Are you good, sweetheart? You're there. Did you already do the settings? Okay, hit escape. Right there. And then 1 for new. And then there. Okay. Are we all here now? Okay. So I want you to choose 1 for add a calculator. And then you should have a screen that looks like this. Oh. You should really only have a 1, 1. I guess it added a new one for me. But so actually your screen should look like, all right. I think I might scream again. Your screen should look like that. Ignore my, you should be on 1, 1. I'm on 1, 2. That doesn't matter. It's because I can't do what you can do. I don't know why, but we will fix that soon. Is everybody here? We all good? Okay, so we want to add another tab, like another page here. This is one very powerful thing about these calculators. So right here, you see this blue control button. You're going to hit the control button. And then right here where it says dock in black, above it in blue it says plus page. So you're going to add a page so you get that same menu back. Okay, are we all back here at this menu? And this time we want to add a graph. So 2 for add a graph. Okay. Are we all here? We good? Okay, so now we need to change some graph settings and then we'll go do what we were really going to do. So while you're on the graph screen, we're going to hit menu. 9 for settings. Then you want this first one to be float 6, not just float 6. Graphing angle, I'm sorry, you're lost. Okay. Are you out of graph? Hit menu. Thank you for saying something. 9 for settings. Then you're here. Okay, good. Yeah, not yet though. Not yet, because there's other things we got to change. Don't get off of the screen yet. Okay, so control, add a page, and I think maybe you had already hit control, so hit control. Dock, yeah, there you go, and 2 for graphs. And then menu, 9. You're welcome. And don't worry about this menu 9 and the setting stuff, because like I said, you won't have to do it over and over again. Once we get it done, we should be good to go. Okay. Escape. I think you might have hit this twice. There we go. And then we want to add a graph. And then menu 9, and you'll be there. Okay. Control, dock, and then 2 for add a graph. And then menu 9. Okay. Are we all here still? Okay. So float 6, auto, really degree doesn't matter. That's not going to apply to us. But then no grid, make sure you have both of these checked. Automatically hide plot labels, show axes and values. I know that there's more check boxes under that. It doesn't matter what they say. Menu 9. Oh, okay. That's okay. If it doesn't show grid for you, that's fine. I didn't realize it didn't show that, but you're okay. Yeah. Yeah, if it doesn't show grid, if it doesn't show no grid, that's fine. Don't worry about it. It won't be a problem. I didn't know that that wasn't there. So if it says that, make sure it says no grid. If you don't even have that, that's okay too. And then, so just make sure that those 3 are right. Make sure these 2 things are checked. We don't care about the rest of them, okay, whether they're checked or not. If you have make default, click make default. If you don't, we just click OK. All right, are we all good with that? Any questions at all at this point? All right. Now, let's go back and look at what we were actually doing over here. So they gave us this function, and we want to know which of the following statements about K is correct, okay? And so we're going to find the rate of change. There's a way to look at it with the graph like we did before, but I want to practice with the calculator and some things and show you how powerful this calculator is, show you what kind of notation you have to have on your paper, that kind of stuff. So we're going to go through and we're going to find each one of them. If I want to find the rate of change for A, right? I'm finding the average rate of change on this interval. And I want the change in Y over the change in X. The Y value, when X is 8.348, is something I would substitute in, right? And I'd get K of 8.348. So I'm going to write down K of 8.348 minus K of -10. Those are my Y values. Over the difference in the X values, 8.348 minus a -10. Okay? Even when you are required to use the calculator, you have to show some stuff. You have to show your setup. Here is your setup. You don't have to put the actual Y values in there at all, okay? But we wrote that down. Everybody with me on this part, yes? Okay. Now we're going to go back to our calculator. Now we're here, or if you don't see F1, that's okay. But if you see that flashing, just hit enter so we don't see F1 anymore. Right? So just hit enter. Now we don't see it. I want to type a graph into F1. I don't have a Y equals button like I did on the other one. And most of this stuff on this calculator is pretty intuitive through the menus and things like that once you know how to add documents. This one to me seems a little bit random, but if I want to get back to where I can type in graphs, you hit tab, which is right above control, and then you get your F1 back. If I had something in F1, it would take me to F2, and I'd have to arrow up if I want to see it, okay? So right here, you're going to type in the function they gave us, 3.16 plus 4.2. Then your X is black down at the bottom. X, Y, and Z are the black buttons down there. Minus 0.85x, and then the squared is right next to the 4. And then double check that you hit all the right numbers. And I'm getting this off the question. I'm not making it up, just so you know. And then we hit enter. Oops. Don't do that. We hit enter when we're done. Okay. Now, although we graphed it, I really don't care about the graph. I really just wanted the function stored in my calculator. And where is it stored? It is stored. So like if I wanted to see when I hit tab, it takes me to F2. It's stored in F1. So this function is called F1 in this calculator. So, and then if I don't need to hit enter or whatever, you have an escape key. escape kind of get you out of there, or you could hit enter, it doesn't matter. So now we're going to go back to our calculator. This big rectangular button right here, you see the left and the right, how they have little tiny rectangular things. They're supposed to be little pieces of paper like pages. So we want to go back to our calculator, so we hit Control left, and that's how we switch through our pages. Okay, to get back to the graph, it would be Control right. We good with that? Everybody here? No. Can I do that again? The graph, okay, the graph is right here on your paper. Yeah, the function. What was your question, hon? No, you're good? Okay. All right, so now, what I'm not doing is typing that function over and over again and entering numbers. Instead, I'm pretty much going to put down exactly what's on my paper. So I want to start with a fraction. So if I do Control divide, it pops a fraction up for me, and I can put stuff in the numerator and denominator. Okay? Then I'm going to type in what we had, which was, and now remember, what we wrote down here is K of 8 point, but I have to call it K here because it goes with the question. If I call it K on the calculator is going to say, I don't have a clue what you're talking about, because we stored it in F1. There's different ways to get to F1 through menus and whatever. I think the easiest way is to literally type F1. See how it changed when you did that? Of 8.348, close my parentheses, minus F1 of, and then the negative sign is underneath the 3. Don't use the minus sign or it won't work. And then you can arrow down to the bottom and then do 8.348 minus a negative 10. Okay. Everybody with me so far? Then the calculator will do everything for you. Did you shake your head no because you're still typing? Okay. But do we understand what to type, I guess is what I said. We're all on the same page. It's fine. It's fine if you're still typing. It's okay. Did you get caught up, sweetheart? Are you still typing your function? Okay. Are you having trouble? What are you doing here? You're not even doing anything. Okay. Well, then you should have gotten one of mine because now you're not going to have a clue what's going on. Okay. Good. Okay. So then when I hit enter, it gives me that slope. I didn't have to do any of that by hand. Okay. And now that it's stored in there, I can do that over and over again. Now, let's talk decimals. The AP rule for AP Pre-Cal and AP Calculus is you have to be correct to 3 decimal places. For stats, I think it's 4. Why it's different, I don't know. It doesn't even matter. You have to be correct to 3. You can write down 10. It doesn't matter. I wouldn't suggest that. And then you can either round or truncate, which means you just chop off the end. We are not rounding because some of y'all don't know how to round and you make stuff up. And so we're just going to truncate because it's okay to truncate. Okay? So, but at the same time, I like to truncate at 4 because it still gives you that extra number, which you can, if you did round, maybe it wouldn't, and you rounded wrong, it wouldn't affect you. And in this case, since we put this on float, if it did have a ton more decimal places, I'd see a bunch more. So really, I have exactly 4 here. We're going to write them all down. So this gives me 5.6042. Did everybody get that number? No, you did not get that number. Why did we not get that number? Do you have... Why does your F1 look weird? Well, I don't think you have... where did those numbers come from? Yeah. I'm not sure what's going on there. Check your F1. There's something way off too. .16. Okay, because you have 4.8 here, not 4.2. Oh, yeah. Okay. Double check your function. All right. We're going to stop here for today because there's not a whole lot of time to do much more. To turn your calculator off, which I don't think I can actually turn mine off because I can't do a lot of what you can do. See where it says the on button with the little house? In blue it says off, so you do Control on and it will turn it off. Mine won't turn off, but yours will turn off. Okay, we good on that? Any questions? Awesome. All right, we will start here tomorrow, so don't lose your notes.